when a photon goes through A or B, it spits out an entangled pair of photons. So for the B path, it has a certain path it follows the entangled pair as one half of the pair gets registered on the screen. The other half of the pair takes a much longer route, goes through a prism, hits a half-silver mirror, and gets detected. And there's an 8 nanosecond delay. And the same thing for the other path. So you're detecting which path information, which path of information, because you know if it hits D3, it came from A. If it hits D4, it came from B. Because these are half-silvered, half of the time, the photons are going to go through. And that's when they get to the erasing portion. This is why it's called the quantum eraser. Because when the photon gets here, they bounce around again, half-silvered mirror, so it can either get detected, this path B can either get detected D1 or D2, because it can bounce up or it can come down. Same thing for path A. So it's not erasing which path information, it's obfuscating it. It's not allowing you to know what the which path information was. Now when it gets to any of these detectors, the time at which it hits a detector is recorded. And the time at which the entangled pair hits the screen is also recorded. So that once all the data has been compiled, then you can analyze the data by first plotting on the x-axis where all the quanta was detected and at what time. And since you know what time the photon hit the screen here, you can look to see if its entangled pair, which detector its entangled pair registered. And then you plot, for instance, for D3, you plot which of these photons were detected by D3, and you plot which were detected by D2, and so on. And of course, D2 and D1 have no which path information. Only D3 and D4. Once you've separated out the points, and when they're detected, you see that photons that had no which path information forms a fringe pattern. Particles that were detected with which path information forms a particle pattern. By the way, they didn't use D4, they just needed D3 for their data. So, that's how the delayed choice quantum eraser experiment works.
Almost experiment. This was done in the early 1900s. Okay? 1912, 1914, 1915, that sort of thing is when quantum mechanics really was born. So it's the early 1900s. So you see, we're almost 100 years away from that now. Okay? And in the 5 or 10 years after these experiments were done, it's my opinion that physicists understood the nature of reality better then than they do now. Okay, so we haven't actually gained much ground in all that time. Now we've gotten a whole lot better about computing The quantum mechanics of today is far superior to the quantum mechanics at that time, but that's all about computation, not about understanding what reality is like.
Seen in, you assign a number, and that number is the amplitude, the wave function of the particle. That's what reality is, according to quantum mechanics. And it's not just philosophy or math, we can see it. Niels Bohr would have told you that electrons and atoms move in circles, kind of like the solar system. Real quantum mechanics, as we now know it from Heisenberg and Schrödinger, says, no, it's not like that. There's a cloud, and this cloud is an actual photograph. This is data. This is a very, very careful physics experiment that has gone in and seen exactly where the wave function of an electron is in this particular atom. So it's a completely different view of reality. The question you should be asking is, why does reality look normal to us at all? Like if really reality is a superposition of all these different possibilities, why do we see things in locations? Why do I look at a chair and say, there it is? Why don't I see a probability cloud all over the place? We don't know. That's what we were taught as youngsters, and then came along quantum mechanics. And I'm not going to give you the full, detailed historical sketch about quantum mechanics. Unlike Newtonian physics, which burst from the mind of Isaac Newton, there were predecessors, but he really figured it out all at once. Quantum mechanics had a difficult birth. It took many people over the course of years to figure it all out. So this slide is just to let you know, to remind you, that the crazy ideas we're going to be talking about in the rest of the talk were forced on us by trying to understand the data, okay? They're not things that we sat around in our room late at night with a few pints going, man, what if there were like a lot of universes out there, okay? We are driven to the crazy ideas I'm going to be talking about today by trying to account for what we see in nature. So for example, there was Max Planck, who was really launched the quantum revolution by trying to understand the radiation of hot objects. We had a theoretical understanding of that, but it was all wrong. And Planck said, well, maybe when light is emitted from these hot objects, it comes in discrete packets. But it wasn't until Einstein, 5 years later, that he said, maybe this light always comes in discrete packets. The difference is, what Planck said was basically radiating body is like a machine that makes you 1 cup of tea at a time. Einstein said maybe tea only ever comes in 1 cup increments. That's a much more radical idea. Maybe what we thought was a wave is really more like a particle. Meanwhile, Niels Bohr realized that if you believe electrons orbit in atoms, they should spiral in and all atoms should collapse in a tiny fraction of a second. So he said they don't for some reason. It's very, very mysterious why Bohr says that they shouldn't collapse. But then Louis de Broglie came along and said, well, maybe it's because the particles that we think of as electrons are really waves. So you see what's going on and why it was so confusing. Einstein said maybe waves are really particles. De Broglie says maybe particles are really waves. It wasn't until the late 1920s that we basically figured it all out. There were 2 people who figured it out more or less simultaneously. It looked very different, but we later figured out it's the same theory, Heisenberg and Schrödinger. And they said, put aside the idea of a particle with a position and a velocity. Invent something new, which we call the wave function, this Greek letter psi. There's not going to be a lot of equations to talk, but I think I should show you this one equation. This is Schrödinger's equation. This is the equation that tells you how a quantum mechanical wave function evolves with time.
It's being fluffed up, so ignore it. I don't care whose mouth it comes out of, president on down. It's not real. Nothing is real. Let me put a perspective on this, another one. How about if, let's say, your neighbor next door got a big fat credit line, several tens of thousands of dollars, and he's completely broke, but he just happened to borrow all this cash, so now he went out and he bought himself a brand new BMW. He went out and he got himself all kinds of new stuff for the house. He got himself a brand new suit. Looking real good, looking real strong, isn't it? Doesn't he? Well, however, the guy is completely broke and in debt now beyond his eyeballs. Does that sound strong to you? Because that's exactly what's going on here in our economy.
I think I like to think of the multiverse as a prediction rather than as a theory. I know that when we talk about philosophy of science or the public perception of science, we sometimes try to be careful about distinguishing between theories and conjectures and hypotheses, but working scientists don't really take those distinctions very seriously. To say I have a theory or I have a hypothesis, it doesn't really make any difference. There is an important difference between a theoretical idea that you would put forward and then try to test versus a prediction based on some theoretical idea. So you could imagine people going around just saying, well, I wonder whether or not there's a lot of different universes out there. And that would not be very interesting. Scientists would not really take that very seriously. But instead, what we have with the multiverse is other theories like inflation, quantum mechanics, superstring theory, that we believe in for totally other reasons. What we find is that these theories predict the existence of some sort of multiverse. So
that's an important thing. Verifiability and repeatability is a hallmark of real science. So we have seen the possibility of time travel into the future. Now, it's actually even on a more dramatic scale when we look at subatomic particles, because there are some subatomic particles that only live for a fraction of a second. Now, I know most people have heard of this thing called the Large Hadron Collider.
That's right.
They have in CERN. Okay. The thing is that the purpose of that Large Hadron Collider was to actually smash these subatomic particles together in order to understand fundamental forces of the universe, and in particular to see if there was this particular particle called the Higgs particle, which is actually sort of gives mass to some of the other particles and sort of acts as a glue for some of the forces. The thing is that whenever they turn that machine on, they accelerate these particles close to the speed of light. And some of the subatomic particles that can only live for normally just millionths of a second, they have been able to show, and they do this every time they use the machine, that they are able to have these particles live for 10 to 20 times longer than they normally would. What that means is that they are, in effect, sending these particles into the future. So the Large Hadron Collider is sort of acting as a time machine for subatomic particles.
What is your idea then for time travel? Because obviously light does play a part in your theory as well, doesn't it, of creating gravity?
Oh yes, in fact, that is the key portion of my theory. I mean, what I realized, see, in Einstein's theory, this is another thing that makes it different from Newton's theory. In Newton's theory, the only thing that can create gravity is matter. For example, the Earth creates a gravitational field which keeps us anchored to it. The Sun creates a gravitational field which keeps the Earth in orbit around it. Thing is, however, is that in Einstein's theory, not only can matter create gravity, but it turns out that light can create gravity as well. That's a fundamental aspect of Einstein's theory, and that was the key to my breakthrough. Because what I realized is that, and you can see the logic of it, if gravity affects time and light can create gravity, then light can affect time. So by using light, we can actually manipulate time based on Einstein's general theory of relativity. Now, I should mention I'm a theoretical physicist, and so what I had to do was first learn Einstein's theory. But then what I did was I had to actually create a theory in which what I wanted to do is to see if it was possible to manipulate time in such a way that it was possible to go back into the past. And I was able to do that. What I realized is that if you create a circulating pattern of light, and by that I mean if you take light and you get light to move around in a circulating path, and you can do that by bouncing off mirrors or having more than one laser. You have several lasers, you can create a loop of light, essentially. And this loop of light will actually allow for the possibility of time travel back into the past. Now, I should mention that in Einstein's theory, what we call the gravitational force is actually a property of space. That is to say that what we call the gravitational force is actually, in Einstein's theory, a bending of space. It's actually a property of space. And so this notion of space and time are linked to each other. That is to say, in Einstein's theory, when you bend space, you actually bend time. And that bending of time shows up as time slowing down. And if you could twist time, okay, then you might be able to go back into the past. Now, when time travel happens, and it will happen, that's one of the things that I try to get people to be sensitive about, is the fact that it's going to require a huge responsibility on our part. It's not going to be, it's never going to happen that everyone's going to have their own particular personal time machine. That would be like the equivalent of saying that everyone has their own particular reactor.
And I found an exact solution for one cosmic string, what the geometry around one cosmic string would look like. And William Hiscock found the same solution independently of me, so we're given joint credit for this solution to Einstein's equation. And then later, I investigated two moving cosmic strings, what an exact solution would look like if two strings were to pass each other. And I indeed found an exact solution for that geometry. And it turned out that if the strings were moving fast enough, but still slower than the speed of light, that this was a solution that would allow you to circle around the cosmic strings and arrive back home before you started. And arrive back home before you started. So it would allow time travel to the past. And there have been a number of general relativity solutions like this. The first one was found by famous mathematician Kurt Gödel in 1949. It's a rotating universe that we don't live in that kind of universe, but it's an interesting solution to the equation that allows time travel to the past. And if there's one solution like that, there could be others. And then Kip Thorne and his associates found wormhole solutions that allow time travel to the past. So it's extremely interesting that these equations of Einstein's with general relativity themselves, and this is our best theory of gravity at the time, seem to allow solutions that allow time travel to the past. So I got interested in it just from trying to understand Einstein's equations with objects that we were interested in.
Now, this idea of a multiverse is not gratuitous speculation. No, it really comes out of both experiment or observational physics about the universe and the current theories as best we understand them.
Matter seems like a good place to begin. The solidity of the world seems totally indisputable. As a fixed thing that you can see and touch, your body is also reassuringly solid. But beginning with Einstein, modern physics has assured us that this solidity is a mirage.